morning, students. Today, in this video, we shall define the completely regular space and discuss some of the facts related to completely regular space. Okay. Let us define the completely regular space. You consider a T1 space. Okay, consider a T1 space. Suppose in addition to that, for each point x0 in X and a closed set A not containing x0, there exists a continuous map. There is a continuous map, say f from x to 0, 1, such that f of x0 is 1 and f of a is singleton 0. So by this we mean that f of x is equal to 0 for every x in A. Then we say that X is a completely regular space. That means X is a T1 space in which this condition holds, that is, to each point x0 and a closure not containing the point x0, that is a continuous map f from x to 0, 1 with the condition f of x0 equal to 1 and f of a equal to singleton 0, then the space is a completely regular space. Okay. And immediate to this definition, we shall claim that every normal space, is a completely regular space. Completely regular space. Okay. Let us prove this result. Every normal space is a completely regular space. Once we have proved this result, then we are having a lot of examples for a completely regular space. That is, every normal space is a completely regular space. And we know that every matricial space is normal and therefore it is a completely regular space. And then we already proved that every compact Hausdorff space is normal and therefore every compact Hausdorff space is a completely regular space. So we are getting a lot of examples for a completely regular space. Now, take X arbitrarily a normal space. X is a normal space. To prove that X is a completely regular space, for that we need to verify these two criteria. That is, X is a T1 space, and then to each x0 and a closure to A not containing that x0, there is a continuous map with this property. Okay. But this condition is obvious because X basically a normal space, therefore it is a T1 space, therefore this condition is obvious, no problem. Now to prove this, you take arbitrarily the point x0, in X and a closure set A in X, such that x0 not containing the point. X0 is not a point of A. It's not a point of A. Now, we have to establish a continuous map f from x to 0, 1 with this property f of x0 equal to 1 and f of A equal to singleton 0. Okay. For that, you just recall the statement of Urayson's lemma. Urayson's lemma. Urayson's lemma. So what is that? So you take X is a normal space. So if X is normal and A comma B are disjoint closed sets, then and also you take any closed interval and a comma b be any closed interval, okay, in R, then the lemma guarantees that there is a continuous map, f from x to a comma b such that f of capital A is equal to singleton A and f of capital B is equal to singleton B. That is, f assumes a value small a on the set capital A and f assumes a value small b on the set capital B. Okay, this is the theorem or lemma you can. Now we are going to apply this relation lemma here by taking, okay, singleton x naught as one closed set. Okay, so because X is a T1 space, therefore every singleton set is closed. So this is a closed set. This is a closed set in X, and X naught not in A. Therefore, these two are disjoint sets. Singleton X naught and A are two disjoint closed sets in the normal space. Okay, and take the closed interval as 0, 1. Then the theorem guarantees that. Okay, there is a continuous map F from x to 0, 1 such that, okay, f assumes the value, okay, 1 on the first set, okay, and f assumes the value 0 on the second set. Okay, that is, f of x naught is equal to 1, f of a equal to singleton 0. Which actually proves that X is a completely regular space, because it's already a T1 space. Now, for arbitrary point x naught and a closure not containing the point x naught, there is a continuous map f from x to 0, 1 with the property that f assumes the value 1 on x naught and f assumes the value 0 on the set A. That is a requirement for the space to be a completely regular space. Therefore, every normal space is a completely regular space. Now, the second way, we can prove that every completely regular space is a regular space. Okay, every completely regular space is a regular space. Before that, we shall prove this theorem in the later videos. Whereas I might need maybe more lecturing hours, maybe 1 or 1.5 hours we need to prove this theorem. Okay, leave the detail for the moment. So next result, actually, every completely regular space is a regular space. Completely regular space is a regular space. Implies regular space. Okay. Assume X is a completely regular space. To prove that X is a regular space, the first condition we need to verify is X is a T1 space, but that is already in the hypothesis of a completely regular space. So a completely regular space means basically it is a T1 space in which every point x naught and a closed set A not containing x naught can be separated by means of a continuous map. That is, there is a continuous map f from x to 0, 1 which assumes 1 on x naught and 0 on the set A. Okay. Therefore, basically X is a T1 space. So this implies X is a T1 space. Therefore, X is a T1 space. No problem. Now, to prove X is a regular space, we need to prove that every point and a closure not containing the point can be separated by means of disjoint open sets. Okay. So for that, arbitrarily you assume a point x naught in X, and A is a closed set not containing the point. Our aim is to find a neighborhood U of x naught and a neighborhood V of A, an open set containing A, such that U x naught intersection V is equal to empty. This is our aim. Okay. Now we are going to apply this hypothesis. X is a completely regular space. X is a completely regular space. Okay. Therefore, okay, here is a closed set and a point not in it. Therefore, there is a continuous map. There is a continuous map. F from x to 0, 1. F from x to 0, 1. Okay, there is a continuous map such that f of x naught is 1 and f of a equal to 0, singleton 0. Okay. Right. Now, look at the codomain closed window 0, 1. It is a subset of R. So it inherits the topology on R. It is usual topology on R. It inherits usual topology on R as a subspace topology. Okay. Therefore, okay. Now look at that. 0. So minus 0.5, comma 0.5. Okay. That is minus 1 by 2, comma 1 by 2. It is an open set in R. You take intersection with the set 0, 1. Okay. It is an open set in 0, 1. It is open in 0, 1. This is subspace topology because you have written this set actually an open set in R intersect with the subspace. Okay, subset. Similarly, you consider this interval 1 by 2, comma 1 by 2, that is 3 by 2. Okay, intersect with the 0, 1. Okay, it is also an open set. It is open in 0, 1. Okay, actually, what is this set actually? So, left close 0, comma half is open and left open half, comma 1 closed. So, these two sets are actually open in 0, 1. Okay. Now, your F is continuous map from x to 0, 1. Therefore, fullback of every open set is open, which means that F inverse of 0, comma half. Okay, F inverse of 0, comma half is open, okay, in X, and F inverse of left open half, comma 1 right closed is open in X. Because F is continuous, these two are open sets in the codomain. Therefore, fullback of every open set is open, which means that F inverse of these two sets are open in X. It is obvious that 0 belongs to this set because it is obvious that your x naught is a point of this set because your f of x naught. Oh no, I'm sorry. It is obvious that your x naught is a point of this set because your f of x naught is 1. F of x naught is 1. Therefore, x naught belongs to f inverse of this set. Okay. And A is subset of this one because if you take any point of A, okay, say S is any point of A, okay, and your f of S is actually value as 0. Therefore, it belongs to this set, which means that S belongs to f inverse of 0, comma half. Okay, therefore, every point of A is a member of this set. Therefore, A is subset of this one. So now look at that, we are finding two open sets, namely U and an open set V. U containing x naught and V containing the set A. Okay. Next, we claim that U intersection V is empty. U intersection V is empty. Okay. That is obvious because if you take any point here, if you take any point, S is in U. Okay, S is in U means that your S belongs to F inverse of half, comma 1. F inverse of half, comma 1. Therefore, F of S is a point of the set 1 by 2, comma 1. Okay. Therefore, it is not in F inverse of not in this set 0. Left close the 0, comma half. Okay. Left close the 0, comma f of s not in this set, which means that s is not an element of f inverse of 0 comma half. Okay, so this is your v. We have arbitrarily taken point s in u, okay, and therefore f of s is in half comma 1, left open half comma 1, and these two are the joint sets, therefore f of s not in this set. Okay, therefore s not in the f inverse of this, which means v. So none of the points of u is a member of V, therefore u intersection is in V. Summarize that for a point x naught and a closed set not containing x naught. Now we establish two open sets u and V, one containing the given point x naught and another contains the set A. These two having no common point, which means that every point and a closure not containing that point can be separated by means of disjoint open set, which means that your space is a regular space. Okay. Now we have summarized what we have defined and discussed. A space is a completely regular space. Okay, if a singleton set is closed, and the fact that a point and a closure not containing the point can be separated by means of a continuous function. Okay, right. And then we have proved that every normal space is a completely regular space. Now we establish that every completely regular space is a regular space. Okay. Next, we shall prove that subspace of a completely regular space is also a completely regular space. Okay. So you take a completely regular space, let X be a completely regular space. Completely regular space, and Y as a subspace of X. Okay, we shall prove that Y is also completely regular. Okay, so basically X is a T1 space. Okay, therefore every singleton set is closed in X. Okay, now if you take any point Y naught in a Y, okay, then this y naught is also a point of your x, therefore singleton y naught is closed in x. This argument you have used a lot of times in the earlier videos, which is closed in x. Okay, so here you are having a closed set in x, and take that closed set, intersect with y, is closed in y. It is closed in y, but we know that this intersection is actually singleton y naught. Therefore, singleton y naught is closed in y. So because we have taken y naught as an arbitrary point, okay, and proved that singleton y naught is a closed set in y. This is true for every point in y. Therefore, y becomes a T1 space. Y becomes a T1 space. Now, the second criteria. Okay, y is a T1 space. Now you take a point y naught in y, and A be a subset of y, be closed in y. Okay, be closed in y. We have to establish that this y naught and the closure A such that y naught not in A. That is, every point and the closure not containing the point in y, okay, can be separated by means of continuous function. Okay. Okay. Now the proof proceed as follows. Because A is closed in y, okay, because A is closed in y, A equals closure of the set A with respect to y. A equals closure of the set with respect to y, because it is closed in y. But we know by previous result, this closure is nothing but closure of the set in relation to the set whole set X intersect with y. Okay, we have proved that. We have already discussed many times. That is closure of the set in the subspace. Okay, is obtained by finding the closure of the same set with respect to the whole set. Okay, that is original topology, and take that set A closure intersect with y, then you are getting the closure of the set with respect to subspace. Now, y naught is in y, and but y naught is not a point of A. Y naught is not a point of A. Therefore, y naught is not in A closure. Okay, it is only a point of y, but not in A means that it is not in A closure. Okay. So here, look at that. we are having a point y naught in y and therefore in x. Okay. And a closure, it is closed in x. It is closed in x. Okay. Closure of the set is always closed in the respective topology. Therefore, a closure is closed in x. So here is a closed set and a point not in it. Therefore, you apply the hypothesis that x is a completely regular. For this pair, there is a point and a closed set not containing the point. There is a map f from x to 0, 1, which is continuous, and that f of y naught, f of y naught is your 1, and f at a closure is equal to singleton 0. F at a closure is singleton 0. So f is basically continuous map from x to 0, 1. Now again, you recall that if you are having a map f from x to some space z and y is a subspace of x, then f restricted to this y is also continuous. Therefore, f, we know that f restricted to y, okay, from y to the same 0, 1 is also continuous. Restriction of continuous map is continuous, simply, also continuous. Okay. Therefore, we are having the continuous map from y to 0, 1, okay, and f restricted to y at the point y naught, because y naught is already a point of y, okay, this value is 1, no problem at all, and f restricted to y at this a, we need to verify that it is equal to singleton 0. Okay. F restricted to y of a is f restricted to y of a closure intersection y. But look at the f restricted y is actually your f evaluated at a closure intersection y, on the set a closure intersection y. This after subset of a closure, is actually subset of a closure. This set a closure intersection y is subset of a closure. But on a closure, at every point of a closure, f assumes the value 0. Therefore, here also f assumes the value 0 because it is after the subset of a closure. So, summarize what we have established is a continuous map f restricted to y from y to 0, 1 such that f restricted to y at y naught is 1 and f restricted to y at the set a is singleton 0. Because this means that these two pairs, that is y naught and a closed set in y not containing y naught, can be separated by means of a continuous map. Because this point and the closed set not containing the point are arbitrary, okay, we have proved that for each y naught and a closed set not containing y naught can be separated by means of continuous map, which completes that your y is also completely regular. Therefore, hereafter every subspace of a complete regular space is also completely regular space. Okay.